Okay, so for this one, we are supposed to find the equivalent capacitance at terminals A and B and assume all initial voltages to be 0. So what's a little weird about the way this one is set up is just how you're looking at the equivalent capacitance at terminals A and B. And so what that means is these last two capacitors, these last two right here, those aren't going to be included because they're not part of the complete circuit. Those are open. So we are going to find the capacitance of these. And similarly, if we were looking for the equivalent capacitance at terminal CD, we would ignore that 5 farad capacitor. Okay, so capacitors work opposite of resistors in that if they are in parallel, you just add them together. And if they are in series, you have to use something different. If you have two of them in series, then you could use product over sum. But if we look at our 3, 6, and 3, we have 3 capacitors in series. You can't use product over sum for 3 things. So the equivalent capacitance of the 3, 3, and 6, so the equivalent capacitance of so the equivalent capacitance of these is 1 over 1 over 3 plus 1 over 3 plus 1 over 6. You could also do 2 of them as product over sum and then get that one and do product over sum of that one with the third one. But this equals 6 over 5. Thank you. And so then that gets us it's equivalent to this. Now we have those capacitors in parallel, and when they're in parallel, we can just add them. So 6 plus 6 over 5 is 36 over 5. And this is 5. Now I have capacitors in series again, and there's just 2 of them, so I can use product over sum. So 5 times 36 over 5 plus 36 over 5, and that equals 2.95 farads.
And why again did you only do from 5 all the way to the 6
Because the 2 5 farad capacitors on the end are open. They're open, part of an open circuit. They're not connected to anything.
So are A and B.
Yes, but we're supposed to be finding the equivalent capacitance at A and B. So if we were finding the equivalent capacitance at C and D, we would use the 5 farads, but we would not use the 5 farad over at the A and B side.
And so it's like part of that one.
Yes. Kind of, yes. Yes. Okay, so now we're going to find equivalent inductance, and inductors add like resistors. So if they're in series, you add them, and if they're in parallel, it's product over sum. So these are all 10 millihenry inductors, but I'll plug in the 10 millihenry after we've added them all. We'll just call them L right now. And you can see that this one that I've circled and this one that I've circled, those two are in series. So since they're in series, I can add them together. And when I do add them together, they become 2L, and you can see that they are in parallel with this vertical inductor right here. So the two that I have circled, I added them together, they became this 2L. And I still have this diagonal L and the bottom diagonal L and those L's. Now this triangle over here, these two L's are in series. So I can add them together, and that becomes 2L. Now, I now have 3 inductors in parallel, but it's easy for me to look just at the last two. When I have 2 inductors or 2 resistors in parallel and they're identical, the equivalent inductance is half. And so a 2L inductor in parallel with a 2L inductor is equivalent to an inductor that's just value L. So I just put these two together. Now once again, I have 2 inductors in parallel that are identical, and so the equivalent inductance is half. Or 0.5 L. And now I have 3 inductors in series, so I can just add them all together. So L equivalent is 2.5 L, and L was given to be 10 millihenries. Which is 0.025 Henries. Let me go get a